All right, homework 3, 4, 5. Homework 4 is here. If you put your name on the section, if you put your section time on the homework, as I've been asking you to do all semester, I have it. If you didn't, I don't. No. We will probably, did you resubmit it for a regrade, or have you just not picked it up? Maybe we'll give them to Bob on Monday. We'll figure something out. I meant to bring it up, and I'm sorry that I didn't. Yes?
You didn't write our section on it?
I guess I'll bring them. Do you want? Do you really want it now?
No, I just wanted.
We'll get it to you. We'll get it to you. Generally in section. Yeah, that's the other thing. They will eventually be moved to a shelf in Corey 297 or brought. I know that last Wednesday, or maybe this Wednesday, Saurabh brought, or at a recent lecture, Saurabh brought some of the homeworks to class. So we'll get them back to you. Where are my notes? Oh, crap. Oops. Take it on. Oh, good. All right, let's get started. Put them in the, okay. Homework 5, in order to not be late, submit it into the box by 4 p.m. today. Would you like it to be due now? Raise your hand if you want to do now. Wait, why are you, why, no, why, all right, well, I mean, look, just, it's due 4 p.m. today. All right, so let's get started. 29. I don't want to use this pen. All right, let's get started. Today I'm going to be talking about frequency response, handling some questions that inevitably you'll have. A quick administrative note is that Project 2 has been handed out or been posted. It is due a week from Wednesday, so you have 12 days to do it. By and large, it has a lot of the same specifications as Project 1. That was intentional. Except that now you're given a power budget, and you want to maximize your 3 dB operating frequency. Okay, so now you're trying to maximize speed. So kind of the design optimization is going to be a little different. You might use some of the other things you've learned to change your architecture a little bit. You could very well conceivably use an identical architecture to what you've used before. Chances are, if you did a good design for Project 1, it will be slow, because Project 1 didn't have any frequency response criterion. So if you did a 2-stage design, your first stage probably consumed very, very little current. So it has very low GMs and big R outs and all that other stuff. So it wouldn't be able to drive the second stage with any kind of decent frequency response. So you'll need to tweak some stuff. That's one thing. The other main thing is that we've added another specification that basically now VDD, your power supply, it's not a specification, it's a condition of simulation. Your power supply is not fixed. It'll be one of 2 supplies. And the reason we did that is for bias robustness. Now, if we can go back to the overhead, what a lot of people did for their bias circuit is some variation of this. To generate their bias current. some number of back-to-back diodes. It might have been stacked diodes, whatever. Some diodes, because diodes take a lot less area than resistors, and you size them such that you get the exact right current flowing through this. You know, you get your desired I, so therefore these output guys have desired I. Now, you know, under the parameters of the first project, that was a good thing to do because diodes are very small area. Now what happens, however, is that now this VDD is going to change a lot. I forget, Saurabh made the project, so I don't know the exact specs, but let's say it's nominally 1.2 volts. It might be 1.1 to 1.3, okay? So that being the case, if you look at this master bias generating structure, the current, so I 1.1 versus I 1.3, the current is very sensitive to supply. So the current with a 1.3 volt supply is going to be a lot bigger than the current with a 1.1 volt supply. So if you make a bias circuit that doesn't have good power supply rejection, then your bias current is going to vary all over the map as you vary your supply, and as a result, that'll make it's another thing that's changing in your design, and that'll make it hard to consistently meet all your specifications all the time. Okay. So that's my quick note about Project 2. Start taking a look at it and posting questions to the news group if you have any other questions. How many people have printed out and looked at Project 2? So very few of you. Okay, so just a handful. That's fine. Look at it, you know, try to look at it a little bit over the weekend so you can get cracking on it next week. Okay. So let's get started on actually covering some material. I'm going to talk about frequency response, as I mentioned before, and talk about, you know, the very primary topology that you'll see when you're calculating frequency response is some variation of the common source inverter. And you see that in your homework. RS, RL, CGD, oops, CGS, CGD. I'm going to call this C out. Okay. So this is a very basic topology, and you've got, you know, I put in these resistors. Who knows exactly what these resistors are going to be? This RS might be an actual resistor, a source resistance coming from your voltage source, but it also could be, in the case of your homework, you know, this guy could be driving this node, and so RS is R out of this device, right? Could be, the RS could be from a multi-stage amplifier. Similarly, RL could be an actual load resistance. It could be an R out of a PMOS transistor. It could be the R out of a cascoded PMOS transistor, in which case this resistance is very high. What I'm basically doing is lumping in all the resistances. So this includes, if we call this M1, this includes R out 1 parallel everything else. Okay, just to really keep things simple. Okay, to sort of simplify it down to the core circuit. Now the question is, well, okay, so what are the poles of this guy? And you can do a lot of analysis, and the analysis gets very difficult or very just tedious very quickly using small signal models. And if you do that, a suggestion that I always do is that I replace all the resistances and impedance and capacitances with generic impedances. So if I were to do this, I'd call this, you know, ZS. I'd call this, you know, ZGD, just because ZGD is more compact than 1 over j omega CGD, and you know, do all the mathematics and then plug in what your actual impedances for each of those branches are. I like that technique. You don't need to use it, but I think that if you were to do it, you'd be happy doing those substitutions. Anyhow, That's still too tedious, so we want to start using some intuition in the case of what's going on. So I've already messed this up enough, so let me just really quickly redraw it. And I'm going to simplify things even more, or make things general even more general. Oops. This is a C3, and then also we've got RL, V out, V in, V out. So exact same figures before, except now I just call them C1, C2, C3, and put the RL to a small signal ground. Same circuit as before. You can keep what you had before if you want to. So now let's think about what the poles are. And the poles really are dependent on, like, the poles interact, okay? And the way you can understand that things are interacting is that the input and output is interacting because of this C2 node, this C2 branch. This capacitor directly couples the input and the output nodes. If this were gone, if C2 were equal to be 0, then calculating the two poles would be trivial. It's RS, one pole is RSC1, right? You've got a pole here. And then you've got this ideal transconductor with no communication between input and output, and the second pole would be C3RL, okay? So that's easy. But that's typically not the case. And what Professor Broderson sort of showed is that if you have an amplifier, that this device does a couple of things. First thing is that the capacitance gets Millerized, right? That in general, if you have an amplifier, A, that has a gain of negative A, okay, and you have some general impedance across it, Z2, from input to output, or Z, I don't know why I called it Z2, that if you then look at Zn is equal to Z2 over 1 plus A, right? Now, how does that translate to the fact that the capacitance gets bigger? That's because capacitance is a form of admittance. Admittance is 1 over impedance. And admittance is complex conductance. Impedance is complex resistance. And so, Yin is equal to Y2 times 1 plus A. So Zn in this case is 1 over j omega c over 1 plus A, which is how you see 1 over j omega c times 1 plus A. That's how that effective capacitance, and I realize I wrote that too small, and I apologize. But that's how that effective capacitance gets Millerized, okay? So, question one in analyzing a circuit like this is, how many poles are there, okay? I told you there are 2 poles, and you can sort of guess that there are 2 poles because there are 2 nodes. Well, there are 3 nodes, but this node here is connected to an ideal voltage source, right? So it's not going to have, it has 0 impedance connecting it to a small signal ground, so it won't have a pole. Now, how can you figure out what how many poles there are? And there are a couple of different ways, and there's a way that I learned by looking at some other material that really is intuitive and easy. And it's figuring out how many, what's the best way to say this? How many of these capacitors in a DC sense can have an independent voltage set across them, okay? And what do I mean by that? I mean that, let's assume that at a snapshot in an instant, a snapshot in time, these capacitors could have any voltage on them independent of what the overall voltages on the other terminals are, because these capacitors are storage devices. The more storage devices you have, the more poles you have. So let's look at this. In this circuit, and I hope I'm not confusing you by talking about this, we've got 3 capacitors. So one could say, well, that means that there should be 3 poles because each capacitor can have a separate voltage, an independent voltage across it. That's not true, because if you just draw the capacitor network, you've got this, C1, C2, C3, right? Now, you can't independently set, you can set C1, the voltage across C1 to anything, you can set the voltage across C2 to anything, but once you do that by KVL, you've clearly set the voltage across that third capacitor, okay? So that's a handy way to look at a circuit and say, how many poles are there, okay? Another way, more generally, is how many capacitors are there will generally tell you, although in this case it'll mislead you. How many nodes there are is a general indication, because the nodes will also, I mean, in this case, it's because there are only two interesting nodes connected to capacitors that you're limited to two poles. Anyhow, but a more rigorous method is to actually do this, and anyone who's interested as to why that's the case, I can talk to offline. So boom, we know we've got two poles. And typically what we do is we identify the dominant pole first. And it's kind of a chicken and egg thing because you don't necessarily know what the dominant pole is until you've calculated all the poles, but you can't calculate all the poles until you know what the dominant pole is. And that's because of that nasty interaction. But you make some basic assumptions and then you check it, okay? So let's assume that we know that this output cap is relatively small, okay? So we sort of know that because this cap is going to be relatively small, then the pole is not going to be at the output. The pole is going to be at the input. All right. So in order to calculate the pole, so the dominant pole, and I express poles in terms of time constants. And basically the time constant is 1 over omega pole. It's just a definition. And that's just because then I can express it as a sum of RCs rather than 1 over a sum of RCs. Same thing. We know that the resistance is RS that we see. Now what's the effective capacitance we see at this node? We see C1, and we also see C2, but C2 is Millerized. 1 plus A. What is A in this? 1 plus GM RL. Okay. Now, I've already made one approximation here. Can anyone tell me what the one approximation I've made here is? I'm sorry? Yeah, except that I already lumped R naught into there. So ignoring that. What's that? Exactly. You're assuming that the gain is your DC gain. And why that is a false assumption, another way of putting it, is that what is the gain through this? It's not GMRL. It's basically GMZ out, right? And this C3 will load down your circuit. So if the impedance through C3 is very small, the gain won't be 1 plus GMRL. And that comes into play when here I'm assuming C3 small. If C3 were big, then this assumption is invalid. Then this assumption here is invalid. But I've explicitly said that C3 is small. So now we want to calculate the other pole. Yeah?
If it is not small, then will the gain be a complex number?
Yes.
And how do you deal with?
Well, then what this does, I mean, there's nothing here. So there's nothing here that's saying Z can't be a function of j omega and A can't be a function of j omega. This Miller analysis still holds, and it's not an approximation in this case. Z in really is, so Z in more generally really is Z of j omega over 1 plus A of j omega. So now what ends up happening is that if you have a capacitor and you have a frequency-dependent gain, then you'll end up in general with a complex impedance. And things get trickier. That's sort of part of this interaction stuff that's so nasty. That makes the math so nasty so quickly, which is why approximations become necessary. So I'm not saying that you can't make approximations. I'm saying that make approximations, but understand what approximations you're making so that you can expect, if you make an optimistic approximation, then you can expect that the answer that you get is going to be optimistic, right? You're going to get a higher frequency pole. This kind of approximation, assuming the DC gain for this Miller effect, is actually a pessimistic approximation. It makes this capacitor look bigger than it is, which brings a pole in. Okay? In actuality, this capacitor doesn't get multiplied quite as much, so that pole will probably at a slightly higher frequency. Now, however, the caveat there is that there are a lot of other approximations that you're making along the way that might be optimistic, so, you know, they all sort of jigger out. Okay, so that's the first pole. Now, what in office hours, what just about everyone who came in to talk about the homework got tripped up by is, in this kind of circuit, what's the non-dominant pole? It's at the output, right? So at the output, so the assumption here is that C Miller is the dominant, right? That basically this C2 1 plus GMRL, this is C1, this is C2, is going to be the dominant factor. So now, at the output pole, I'm going to just redraw the circuit. Oops. Okay. So now we're trying to calculate the pole at the output. And the quick analysis would be, well, it's RL C2 plus C3. And C2 has some slight Miller, 1 over 1 plus A. Okay. But basically, tau 2. This is wrong. Okay. And does anyone who wasn't in section, because I told people in section the answer, want to take a guess as to why this is wrong? And Professor Broderson alluded to this in class. Okay. So that means that all of you have to correct your homework after class because you all got it wrong if you don't know the right answer, or you're just too shy to volunteer the answer. It's because this capacitance is being Millerized. So basically what's happening is that this capacitance is being made to look like a very big capacitance. So once you get beyond that frequency, this capacitance just looks like a short. Okay? I just made a weird logical leap, and I see a lot of confused expressions. Do you want to ask, are there any questions as to the logical leap I just made? Yeah?
I thought when you Millerize it, you put C2 to the ground on the other side. Like C2 parallel with C3.
Mm-hmm.
Right? Because the gain is the Miller effect is not a lot. It's like 1 plus 1 over A.
Yeah, and this really comes down to how big C2 is. Okay, if C2 is big, then at the higher frequencies, this capacitor will look like a short. Right? So at high frequency, I mean, yeah, you could just put this over here, but the point is that at high frequency, you're looking in this direction, you see this node. If all you were to do was do this, C2, C3, RL, that means when you twiddle this node here, you don't get any changes over here. But that's not true because this capacitor provides a direct propagation path from the output back to the input. And the point is that that's gonna change the nature of the circuit analysis. Yeah.
Assuming that C3 is really small?
What's that?
Is C3 still small?
C3 is still small, yeah. Like RL, yes.
So this is after you go in and you calculate CGB and you find that it's huge.
Right.
Then you know that, oh, it's going to get shorted out.
Yes. Because, I mean, this capacitance is getting Millerized. So it starts acting at a very low frequency, right? So it looks like, and when capacitors start acting at when they start acting and start limiting the bandwidth, what they're basically doing is providing low impedance paths, right? And when they provide low impedance paths, that's what kills the gain. But if they provide low impedance paths, that also means that you can talk both ways through them. So stuff that goes on at the output is translated back to the input. Yes?
So we have to see that CGB is actually
Yeah, that's basically the condition. There's also, I mean, but it also is that CGD gets Millerized, right? Okay.
How can we tell though, like how much bigger is bigger?
That's a really good question. I don't have a great answer for you, which is why these approximations for non-dominant poles will sometimes be off by a reasonable factor. Yeah, I mean, because yeah, this is an approximation that I'm making because I'm making a very simplistic approximation in terms of what kind of interaction is going on. In reality, there's much more complex interactions going on, and were you to pull out the small signal math, you'd have second order polynomials that are really hard to derive any intuition from. Yeah.
But if C1 is fairly small, then it shouldn't really affect your calculations that much,
Well, it does. Here's the thing. Okay. So now let's assume that this is a short. Let's assume that C2 is just big, okay? Even independent of the Miller effect. Let's just assume C2 is big. Okay, and that's actually the major assumption that you need to make. Okay, so if C2 is big, then no matter what, like once you break beyond this, C2 is going to look like a short before C3 does, right? So and before C1 does. Okay, so this looks kind of like a short, then the question is, well, clearly what capacitances do you see? You see C1 and C3, right? So in calculating your tau, you're going to have some R times C1 plus C3. Okay? What does the resistance look like now? 1 over GM. This is now a diode-connected transistor. It's actually 1 over GM parallel RS parallel RL. Okay? So now what happens is, yeah, versus what I had said before, RL times CS plus C2, C3 plus C2. Now, C1 might be relatively big because there are lots of other things hanging off that node. So your capacitance might go up, but your output impedance goes down quite a bit. Okay? And realistically, I actually have to correct myself because I don't want to mislead you guys too much, but this really is the case when C2 is big, not really when the Miller effect is big. Okay? So in your homework, it might actually be that the Miller effect does that C2, you don't short out C2. Yeah, it is pretty small. It is pretty small. So you gotta okay. So with that caveat, you kind of have to take that into account. So let me just look at my notes real quick. Okay, so that's really the case when C2 is big.
So when C2 is not big, you use the other case.
Right. Well, it depends on what else is big. Okay. So now, because this is what you have to do in the homework, now let's look at the case that when C3 is big. Okay. So we've got, I'm going to redraw it.
For the previous case, David?
Yes.
Is it diode connected in the aspect that the gate voltage and the drain voltages should be treated the same?
Yeah, because that node ends up.
Like a diode connection.
Yeah, it is a diode connection. I mean, you're connecting the gate and drain. Okay. Okay. So now C1, C2, and I drew C3 to be particularly large. Okay. So now what's the dominant pole here? The output. Yep. So tau 1 is just equal to RL, and the capacitance seen is basically C3 plus C2 times 1 over 1 plus A. Okay? basically RL times C3 plus C2, which actually really roughly, in this case, is going to be equal to RL times C3. Okay. Yeah.
So I had a question. When you said that, when you asked that question about the VVD,
VGD.
the VGD,
Yeah.
but then you have the same current and then you have the same W over L. That means, how can the value change then? I mean, because if it changed, now you're
But there's small signal currents flowing around, so there's small signal currents flowing around which allow for the gate and drain voltages to change.
Okay, well, okay.
And they're not exactly the same, they're approximately the same. There's small signal currents flowing around, which is why the voltages change anyways. Okay?
Oh.
So getting back to this, so the dominant pole is RL times C3, right? That's pretty easy, or roughly speaking, RL times C3. So the question is, what's the non-dominant pole? This could be at the input, right? So the resistance seen is RS. C2 can't be necessarily treated like a short yet. So what capacitance is seen at RS? You see C1, and then what happens to C2? Does it get Millerized? Yes, no. No, it doesn't. And the reason why is because if you look here, this capacitor, it gets Millerized, but to a much lesser extent. And this was the assumption I was talking about before. This capacitor kills the gain here because this capacitor at frequency looks like a very low impedance node. So this looks like a low impedance node. As you go higher in frequency to find the secondary pole, this is going to look like a really low impedance node. So to the limit, what you've got is that the capacitor now just looks like a short. And so now you have this. Okay. So there is some Miller effect, but not really. And you can make an approximation that there is no Miller effect. So you get C1 plus C2, and you can still say 1 plus A, but A goes to 0 in the approximation here. Now here, you can see that I've made an optimistic approximation. I've assumed that this node is a ground, that there is no Miller effect. In reality, there will still be some residual Miller effect, and there will be some complex impedance here, so you'll have some gain from input to output. So this capacitor will sort of look bigger, but we're making approximations to keep the interaction, the mathematics of the interaction, relatively straightforward. Yes.
C3 is an intermediate bond. You can't call it large, you can't call it small. How do you,
Okay.
for example, in a project.
Yes. You're absolutely right. You're absolutely right. Now here is where, okay, this is where I differ from the instructor a little bit in terms of methods to use, because I didn't take 140. I took a class somewhere at MIT. So whatever. I didn't go to MIT, but I took a class at MIT. There I learned to do zero value time constant analysis. And zero value time constant analysis, when you're talking about open loop amplifiers, where you basically sum up all the small poles and sum them up together to get one big pole, is really useful when all those capacitors are intermediate. And Professor Broderson talked about it briefly. Like in my class, I spent around, I think, 3 weeks on zero value time constant analysis. And that's actually a really good segue. But I'm going to hold off on it for 10 minutes because I wanted to talk about something else. So in the intermediate, in the case that all the capacitors are roughly equal and the Miller effect doesn't dominate and you can't tell what the dominant pole is, do a zero value time constant analysis. And then if still all those individual time constants are on approximate levels, then the zero value time constant analysis can be really useful. If you find that you do the zero value time constant analysis and then boom, one of these time constants is way bigger, in other words, the pole associated with a capacitor is way smaller, then you know you're onto something, and you can sort of move forward by making some of these approximations. Okay? So one point I wanted to make was and Professor Broderson spoke about this as well, was the use of cascoding for high frequency design. Okay? So what we know is that when you have this RL GM, you've got this single device. You know that we get Miller effect, right? And that really, really limits the bandwidth. Now, what can we do to avoid that? We can avoid that by using a cascode. So if we now say, and the reason why this Miller effect happens is that this capacitor provides direct coupling between the input and output. Okay, so if you can break that coupling path, then you're in good shape. And this is what you had to do on your homework. So let's assume that this guy is just tied to some battery. So it's tied to some bias. So now you still have this capacitance going from here to here, right? And so there will still be some Miller effect. Okay, so I've just drawn the primary capacitances. And yeah.
I have a question about if your voltage tied to your source, you know what's coming?
Yeah, I know exactly what's coming. In your homework, this capacitor is connected there.
So there is a Miller effect present?
Is there a Miller effect present? That's a good question. Not really, actually, because it's positive gain from point A to point B. And the way to look at, and also the other thing is that this node here is a low impedance node. It's 1 over GM, right? So in order for the Miller effect to really happen, like if you just drove this node, right, you'd still have the Miller effect in the capacitance, but it wouldn't band limit you because it's being driven by a very low impedance node, right? Here, this is a very low impedance node. So yeah, there's Miller effect, but it doesn't looking up that way, but it doesn't really affect you. And I think actually in my solution set, I kind of ignored that and did this. And by and large, that won't hurt you very much because at least looking from the output, this is a low impedance node, so it's a low swing node, so it can be approximated as ground. So you can basically just tie that cap to ground. The reason why we tied source to bulk was just to keep VTs the same. In reality, that's not what's going to be done because that will introduce other issues. So in general, the drain bulk capacitances, the bulk will be a small signal ground. So okay, let's look at this. Now the question is, now we have 3 nodes, right? So there are probably 3 poles. And you can actually, if you use the analysis that I had said before, the voltage across this voltage can be set independently, across this capacitor. This voltage can also be set independently, but we have a new node. This voltage can also be set independently. So because there are 3 capacitor nodes that can be set independently, that means there are 3 poles. Okay? So what do I want to do here? The question is, okay, where are the dominant poles? There are 3 poles, and in general, you want to figure out which 1 or 2 are dominant, okay? So let's call this node X, call this node Y, and call this node Z. And I think there's a question. Did someone have a question?
Yeah. How do you know it's 3? Oh, because of the nodes?
Because of the nodes and how many capacitors can be set independently. You can't really just use capacitors because in the simplest case, you can't just count capacitors. Like here, there are 2 capacitors. There's clearly only 1 pole, right? So anyways, okay. So now, if you don't know the relative sizes of the capacitors, what's sometimes useful is to look at the relative sizes of the resistances at those nodes to ground. And what we know is that the resistance here is through RS, right? The resistance here is through RL. Those resistances might be appreciable. The resistance here is 1 over GM, okay? So this is probably going to be the highest frequency pole because all these capacitors will be on the same order. So, okay, so let's look at the pole at node Z, okay? So let me just redraw this. At node Z, we've got this guy to here, this guy to here, RS, and then this here. Okay. So we still know, so this is CGS1, CGD1. Okay? We still know that there is going to be a Miller effect here. Because this is still, there's some gain, so this is going to be amplified by some amount. But the question is, what's the gain from here to here? What's the gain from node Z to node Y? M1, M2. Anyone? It's basically approximately 1. It's GM1 over GM2, A of Y, node Y over node Z equals this, approximately equals 1. Okay? So that means now that we know that, we can calculate the pole. Tau1 is equal to RS times CGS1 plus CGD1 times 1. This is actually, the gain is minus 1 plus 1. So CGS plus 2 CGD, roughly, times RS. Pretty straightforward. Let's actually look at the capacitance at, let's look at the pole at the intermediate node as well. Okay, I think that's all. Is that all the? Yeah, there are actually 2 caps here, but whatever. Okay. So, CGS1, CGD, CGS, oops, CGD1, CGS2, CDB1, and CGSB1. So I'll just lump these 2 together. So, what's the impedance seen at this node? The impedance seen at this node, assuming that RL is relatively small, well, the impedance R is R in, R up parallel R down. R down is equal to R out, RO of that device, which is big. R up is equal to RO2 plus RL over 1 plus GM2 RO2. If we assume that RL is smaller than RO2, you get roughly 1 over GM2, as we said before, which is why it's a high impedance node. So, therefore, and so that's so the R is basically equal to that, and the capacitance. So we get tau 2 is equal to 1 over GM2 times various capacitances. CGS2, CDB1, CSB1, plus, now what happens with this capacitance here? Well, it sort of becomes inverse Millerized. CGD. So this, okay, when this node is swinging in one direction or another, it's because this node is swinging, right? And because the gain is -1, they're swinging totally antipolar, right? So that means that you end up seeing twice the effective voltage across that capacitor, which means twice the effective current, which means that it's effectively 2x the capacitor. Because what we're doing here is we've got -1, like this, right? And we're looking at the capacitor in this way. The relationship is the same as that, right? Oops. So, because it's a low gain, you end up seeing the Miller effect looking backwards. So you end up getting ×2. Okay? And then finally, the third pole is relatively easy, and I'll just keep it drawn here. You've got this cap, you've got that cap, and it's basically RL times this cap, which is CGD2 plus CDB2, tau 3. Okay, and it doesn't really matter how big this cap is because there isn't communication. There isn't that direct coupling, that interaction that I was talking about before. So whether or not this cap is huge, and so you treat it like a short, doesn't really affect the analysis of the other poles. And that's the beauty, because what this is a two-stage, a Cascode amplifier is a two-stage amplifier. It's a common source stage followed by a common gate stage. And the great thing about common gate stages is that you do have true isolation between the input and the output, or almost like very good isolation between the input and the output. The only communication is through R0, which isn't frequency dependent. Okay? So that's that. Briefly, in a few minutes, I wanted to talk about, oh, no. Rather than talking about zero value time constants, yes?
So in terms of the project, when you use those active loads, or
Uh-huh.
you use the primary loads
Sure.
with them, so then,
Do you mean this amp?
the thing on top.
Yeah, the thing on top.
So then you can't really use the 1 over GM, right, anymore? That wouldn't be able to
Well, it is.
G across that.
Well, there's a shunting capacitance in parallel with that impedance, right? In parallel with that 1 over GM resistance, right? I mean, because what you're saying is, okay, so this device, okay, at DC, Rin equals 1 over GM, right? So now we're going to say, well, there's all these extra capacitors hanging off. Okay? So now let's talk about Zn as a function of j omega. Okay? The DC behavior of this guy still holds. So it ends up being 1 over GM parallel. Let's call this C1 and C2. You know, there is that CGD, but that no longer matters, right? Because it's shorted out. Parallel 1 over j omega C1 parallel 1 over j omega C2. Okay. So what ends up happening is that, and you calculate that out, you end up, so let's just say 1 over GM parallel 1 over j omega C1. So that's GM times j omega C1 over GM plus j omega C1, right? Did I do that right? Oops. So multiply top and bottom by GM j omega C1, and you get 1 over j omega C1 plus GM now is equal to 1 over GM times 1 over 1 plus j omega C1 over GM. Okay. So now what you get is the DC resistance, this is Rin, times a pole. So if you were to plot Z in, it looks like that. And I'll draw it a little bigger. So this is 1 over GM, and the pole here is GM over C1. And so basically what that really is you've got the impedance of the GM device in parallel with, if you were to plot the impedance of this line here is just 1 over j omega C1. And so they intersect, and you're limited by the smaller of the two. Anyhow, so what I wanted to do real quick and effectively keep you maybe 5 minutes longer, I hope you don't mind, is analyze a problem that might actually be useful to you. Everyone pulls out their pens. And this is something that Professor Broderson started, so it's possible that he will do this himself. So VID over 2 minus VID over 2. Okay. So I'm going to just draw two primary capacitors here. C2, and C1. Okay? In addition, there's all the CGDs and all that other stuff, but I'm just simple. And there's also this. I'll draw these guys in as well because we'll see. Okay? So ignoring the, so let's assume that this is driven by perfect voltage sources, so there's no poles at the input nodes. Okay, this goes up, this goes down. We know this node is going to stay as a virtual ground, so it stays basically the same. So as a result, GM VID flows in. Oh, what we're trying to figure out, I'm sorry, is V out over V in, as per usual. GM VID over 2 that way, and so small signal you get GM VID over 2 that way. Okay? And so the question is, well, what's the overall frequency response of this? So what we know is that there's going to be some I3 there, okay? So V out is going to be equal to, let's call this I2. I2 plus I3 times Z out, where Z out is the output impedance, is, you know, R out parallel C out, which is equal to RO over 2 parallel C out, because RO up and RO down, which is equal to, so let's just leave it as R out. It's equal to R out over 1 plus J omega C out R out, C2, oops, excuse me, and the capacitance C out is C2. Okay? We know what I2 is. Now we have to calculate what I3 is. Okay? So I3 is, we did this just a second ago. We calculated what Zn going in this way is. Zn. So Zn2 is equal to 1 over Gm2 times 1 plus 1 over J omega C1 over Gm. Okay? And we know that I3 is equal to the voltage on this node. The voltage on this node is going to be I1 times Zn. That's the voltage that gets translated to this node. And then that just gets translated out through the transconductor, Gm. So I3 is going to be equal to Gm2. So I3 is just 1 over, is I1 times 1 over 1 plus J omega C1 over Gm. Everyone see that? Okay. So now, plug that in. So just to recapitulate, I3 equals I1 over 1 plus J omega C1 over Gm, which in turn, we already calculated what I1 equals, Gm VID over 2, equals Gm 1 over 1 plus J omega C1 over Gm2 times VID over 2. Okay. I2, which is this current, is equal to Gm1 VID over 2. So therefore, I out, which is this current, I apologize for jumping back and forth all over, I out is equal to I2 plus I3, which is equal to Gm1 VID over 2 times 1 plus 1 over 1 plus J omega C1 over Gm2, which is equal to Gm1 VID over 2 times 2 plus J omega C1 over GM2 over 1 plus j omega C1 over GM2. That's I out. And this can be simplified. Let's divide this by 2. So this becomes 1 over 2. Divide the numerator by 2 and the denominator. So we put a 2 out here, which gets multiplied by that. So I out equals GMID 1 over this times 1 over that. And so V out is equal to I out times Z out. And you'll see where this is all going in just a second. So V out equals, so Z out is here, R out over this pole. So R out over 1 plus j omega C2 times R out, times, and then this quantity times I out, which is 1 plus j omega C1 over, let's put this a 1/2, or over 2 GM over 1 plus j omega C1 over GM. This is GM2, GM1 VID. Okay, so now here is, let's put this over here, GM1. So V out is equal to GM1 times R out. That's the DC term. That's what we expect from our DC analysis. Okay, now let's look at the poles and zeros. 1 plus j omega over, I'm going to just do a little 2 GM2 over C, 1. That's the numerator here. Over 1 plus j omega divided by GM2 over C1 times 1 over 1 plus j omega over 1 over R out C2. Okay, and I've done this, I've put it in this form to explicitly see where the poles are. So what we see is we've got our DC gain, GMR out. We've got a pole at GM2 over C1. We've got a pole at the R out times the C out, which is C2. And we've got a 0 at twice this frequency. So let's look at this. Let's look at this term. What this term looks like is at low frequency, it's 1. At GM2 over C1, it starts to break. And then at 2 GM2 over C1, it flattens out. So this is 1 and this is 0.5. Okay. And then here, we've got another pole at, 1 over R out times C2. So now, with this expression, let's go back and look at the circuit and understand where it comes from. Okay? So here's the circuit, and here is the frequency response. The DC component we expect. This output pole we expect, because it's the pole at the output. If you were just to look at this and say, what's the pole at the output? You'd say it's C2 times the R out at this node. No surprises there. Now let's look at this pole 0 combination. Okay? What that means is that at some point, this voltage is going to stop moving because this capacitor loads down this node. So at that point, this device, this gate looks like an AC ground. So that means that this always outputs the same current. So this mirror up top and around stops being effective. When that mirror stops being effective, you're just throwing this current through your left device out, and your gain drops by a factor of 2 because your net transconductance is half of what it used to be. So there's sort of like, I went through the small signal math, and there's sort of the sanity check. You look at it and say, okay, am I off? Am I close? Like, did I make a mistake? All this stuff makes sense. So from there, you can sort of see, okay, the math is self-consistent with the intuition. and therefore you've probably got the right answer. So that's it. Have a good weekend. Homeworks are due today.
I can't stand the readers. I know it's not your problem. I just want
Okay.
to tell you. Okay. This I checked with 2 other people.
Uh-huh.
I have the exact same answers that they did, and
Okay.
they all got it right, and I got -4. I can't stand the inconsistency of the readers. I mean, this is ridiculous. This happens every homework, and I have to like turn in for a regrade every time. What's
I
going
don't know.
on?
I don't have the solution set in front of me.
Right. I
don't
mean,
know.
can I actually borrow a white sheet to use for a note for the reader? Because I'm gonna turn this in again.
Sure. Yeah. Yeah. Drop it off in the box, okay?
In the box? Okay.
I have a question about the zero value time constant. It's just for us to low.
It's not cool, man.
No, it's actually, and I didn't get to
4
this
points,
section.
It's
It's actually useful. It's useful for finding the 3 dB frequency, which could be a contribution of lots of poles. So that's that.
It's usually the lowest pole.
Well, it depends. I mean, if you were to hold on.
It's not the second pole.
If you were to have a bunch of circuits, let's say if you were just to have, okay, on and on and on. All the poles are roughly the same, right? And there are a lot of them. There could be like an infinite number of them. Calculating what the 3 dB frequency is kind of tricky, but the math sort of demonstrates that if you add up all the zero value time constant, you'll get an approximation of the 3 dB frequency. Because what it ends up doing is hold on just one second. Do you mind if I use S instead of J omega? Okay. So what you get is in your poles is equal to 1 plus A1 S plus B2 S squared plus dot 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 dot. Then what the zero value time constant will give you, HZV TC, it'll give you the value of A1. So if you just approximate it as 1 over 1 plus A1S, like you're ignoring the higher order poles, but you're doing a Taylor approximation, truncating after the first dominant term. So you're able to actually explicitly calculate that A1 value, and so that's what it's useful for. If you have a dominant pole, then doing some simple analysis is usually sufficient. And if you have one dominant pole and all your other poles are way out there, when you the other poles really have no effect on you, so that's fine. What the zero value time constant really comes in handy is figuring out what that 3 dB frequency is.
Just remodel it again.
To get the second pole,
Yeah.
can't use zero value. As far as I know, you can't use zero value time constant analysis to get the second
Again, he might be.
But the zero value time constant analysis doesn't give you the pole; it gives you the 3 dB frequency.
Like, say
Yeah.
the
There's a
exact same number up to
I just want to
significant
just
digit.
find out where the second pole is.
wrong,
Where the second
dude.
pole is.
That takes circuit
He didn't
intuition.
explain why I got
You have
wrong.
to kind of look at the circuit.
In one of the problems here, I
Who's the
think
reader?
if the
you the reader?
the kata method
I'm sorry. Wait, hold on. Are you asking who the reader is for 141 for 140 is?
It's like Raul or so.
No, 140 is Nikhil Sharma.
Nikhil Sharma.
Yeah, you can send him email. His email address. It's
I
public.
know who he is.
Okay.
I'll talk to him.
If the kata method are comparable to each other, can we use the same method for compensation for finding the second pole?
Zero value time constant analysis?
No, the method for
If they're comparable, then realistically finding that second pole, as far as I know, you kind of have to just do full-blown signal math, full-blown math, and it just gets nasty. I can't think of a better way. Like, it depends on how much area you're willing to tolerate.
so, sure.
All right?
Thank you.
Ask you a question, David.
Sure.
It's the same problem we talked about in office hours.
Okay.
The pole here, assuming that this has been shorted.
Yeah. Yeah, I realize, this is what the solution set says, and I'm actually reusing the problem from the previous year, and I sort of went along with it. Said it's not always the case.
Because is this capacitor big enough?
It's probably not big enough.
Okay, because when I
And
actually
his analysis doing that ended up with a grossly optimistic number. So I think that solution set just has an error, and I'll have to go back and check it.
what would you advise us to do on this one then?
I would say calculate both. See what it's going to be somewhere between the two.
Both
So
are,
if you,
actually both are very off, and the
one's optimistic, one's pessimistic, right?
one's 0.1 gigahertz,
Uh-huh.
and the other, I did a quick math, is 2.7 gigahertz.
Right.
An average of even the
And
average
so
is
what's
higher.
the actual frequency ends up being like 400. It ends up being 400 megahertz. So
Yeah, so this
so
one's
it's
off
it's
by
actually
more.
it's actually sort of well it's between. So the answer is between the two, and the reason and the intuition there you should be say good. It should be between the two because it's somewhere
Those are
between
the-
these two
Those are
modes.
the absolutes, right?
Yeah, those are sort of like the upper bound approximation and the lower bound approximation. You can't treat this as a total short, but you can treat it as a partial short. And treating it as a partial, like what does a partial short mean? I don't know. It means that you really have to do the full-blown signal math, which is too tedious.
Bad.
Yeah, which is bad. So it's somewhere in between the two.
Can we do that for the homework thing? Can we say we can't?
Yeah,
assert the
if you
exact
well
pole,
if you
but
give
it'll lie between in
We
this
give the
range.
range.
yeah no if you do that you'll get that's like perfect. That's better than the solution set perfect.
Unless my reader sucks.
Yeah, unless the
and then
keel
this-
goes gung ho on us, it says.
He's usually been pretty nice. I mean, like I've seen what the average scores have been, and like people rarely get below an 85.
But it's the principle because
I agree with you. If you got the same answer and they didn't, like, is it the right answer?
yeah, because it's like 4 other people got it and they got it.
No. Is it the right answer?
I'm pretty sure.
If it spot checks, I don't
But
know.
either way, shouldn't it be consistent because we're doing on a curve with other people? So that means like if I get the same answer and
Curves,
they get a better answer
curves.
than in the curve, then I get
Listen,
better
Sonny
than
boy, the important thing is to learn the material. Curves. I mean, when I ask people to raise their hand and say who wanted it to be due today, that was a rhetorical question on my part.
wanted to be due today.
Who wanted the homework to be due now as opposed to 4 o'clock? That was a rhetorical question.
They raise their hand.
Some people raise their hands.
You know why? Because they want a better grade.
It's like this whole
bastards.
curve crap. Like just understand the material.
Unfair because people turned it in. Only us and Officer didn't turn it in.
So we get for being diligent.
I know. Wake up early. Stop sleeping.
Wait, that's what you get for being diligent? You weren't diligent. You didn't hand it in before class.
No.
Be
Diligent
diligent
or
enough to go to
going to the
office
office hours because we noticed the difference. Huh? They don't even
this
care.
doesn't correlate. We got to figure out what's going on. We got to ask our man
Nice.
David.
Good spin. Good spin.